pleasure to introduce Paige Novak. She's a department head in the Joseph T. and Rose S. Ling Chair in Environmental Engineering in the Department of Civil and Environmental and Geo-Engineering at the University of Minnesota. Novak's area of interest is the biological transformation of hazardous substances in sediment, groundwater, and wastewater, resource recovery, and particularly how engineers can influence these processes. She has a BS in chemical engineering and MS and Ph.D. in environmental engineering. Paige was an Leopold Leadership Program Fellow in 2009 and has been the recipient of several awards, including the Sarah Evans Woman Scholarship Leadership Award in 2013, the Bill Boyle Educator of the Year Award in 2013. Busy year, huh, Paige? The Samuel Arnold Greeley Award in 2011, and the Paul L. Bush Award in 2007. She was named the Fellow of the Water Environmental Federation in 2016 and of the Association of Environmental Engineering and Science Professors in 2019. From 2013 to 2019, Novak served on the National Research Council's Standing Committee on Chemical Demilitarization. She has recently finished her term as the editor-in-chief of the Royal Society of Chemistry journal, Environmental Science, Water Research, and Technology. Just to finish, I know Paige from a small, it's called a Serendipity Grant from the U of M back in 2016. And we were working with multiple parties, and we were trying to put together a network of organizations that would have online resources and in-person networking, and basically a market for network, including water technology companies, utilities, engineering firms, researchers, consultants, and investors. So, Paige, take it away.
All right, thanks, Tim. Can everyone hear me okay? Okay, I'm gonna share my screen. All right. Okay, I am gonna shrink everyone down. So if you have any questions while I'm going, if something is confusing, well, I'm shrinking all the faces down, just interrupt. It's not a problem at all. I'd rather you interrupt and we clarify something if it's unclear. So I am going to talk today about water, wastewater, energy, and climate change. And I was told that you all have had a lot of talks, or you have a lot of information about energy and climate change, that connection, but maybe not so much on the water and wastewater connection to energy and climate change. And so that's what I'll talk about today. And so hopefully it's interesting and new information, and hopefully I pitch the level about right, but let me know if you have questions or anything like that as we go. So I want to start by talking about the intersection of water and energy, and just kind of putting that out there, how these are related. A lot of times we think about water and energy kind of separately, both of them as resources, but they're really quite interrelated. And so this first statistic is from the U.S. Energy Information Administration, and it's that energy production uses about 11.6 gallons of water per kilowatt hour produced. And so in general, when we produce energy, we're talking nationally, it uses quite a bit of water to do that. And so if we think about that, energy efficiency should really have a dramatic impact on water use. And so this graph right here is, let me shrink down my little floating panel. One sec. Okay, all right, good. So this figure is from the EPA, and it's a little dated. It's from 2010, but it shows different sectors that contribute to U.S. freshwater withdrawals. And one thing that you notice right away is that the thermal electric power chunk of this is huge. So a huge amount of water is used for thermoelectric power generation. Most of this is pass through. So this water is taken up, it's used for cooling water, and then it's discharged. But some is evaporated. And so you do lose some of this water. And sometimes chemicals can be added, and the water is certainly heated during this process. And so the more that you can decrease this, the more that we can start using alternative energy sources, the more that we can become more efficient in our thermoelectric power generation, the more this freshwater withdrawal will decrease, which is a positive. Another link between water and energy is this statistic that about 1.1 kilowatt hours of energy is used to treat and distribute 100 gallons of potable water. And this is about average of what we all use per day. The numbers vary between maybe 70 and 110 gallons per day, but this is about what we use. And so there's a continuous energy required in order to treat the water that we use to water our lawns, to flush our toilets, to drink. Very small amount of that is what we drink, but we all use a lot of energy for our water. And so what follows from that is that our water use efficiency should also have a dramatic impact on energy use. So energy efficiency impacts water use efficiency impacts energy use. And so we want to keep both of those things in mind. And so back to this figure, this water here, mainly the public supply, these self-supplied domestic waters, this is your private well, but this public supply is where the energy comes in. And so there's actually a pretty large withdrawal of water for public supply. And this is where a lot of that energy goes to treating that water. And so this just shows water use in a typical American home. You can see we use a lot of water for showers, toilet flushing, leaks, fair amount of leaking, washing our clothes, other things like drinking, maybe watering our lawn. But you can see that there's a lot of, well, I guess this is indoors, so there's no lawn watering, but there's a lot of water that's used that we can think about maybe decreasing that water use. Certainly leaks, you can decrease your shower, things like that, and that'll decrease the energy use to treat that water in the first place. Another area that we don't think about all the time is manufacturing. And so manufacturing is not really called out specifically in this graph, but I highlighted self-supplied industrial and mining. So there are a lot of manufacturing facilities or industries that use water, sometimes very, very highly treated water, very clean water. And this is another area where there's a large energy footprint, basically, to get that water clean enough to use for manufacturing. And so here's another table that goes through the embodied water in different products. And so you think about a car, there's an enormous amount of water associated with the manufacturing that goes into that car. Smartphone, probably all of us have one of these. We might be wearing t-shirts right now, maybe not jeans because it's hot, but we're all using lots of products, and these products have a water footprint. And then that water footprint also has an energy footprint associated with it. And so, again, just thinking about this link between water and energy, and how the more that we can be efficient with our water use, the more we can decrease the energy that comes from that. And so, hopefully this sort of set the stage of how water and energy are connected. And so, now I want to kind of switch a little bit to one of my favorite topics, wastewater, and talk a little bit about wastewater and how wastewater then is tied in with energy and also climate change. And so this is another statistic that wastewater treatment accounts for about 2% of US energy use, and it contributes a huge amount of CO2 in treatment. And I'll go through that in a minute. And so we think about the water that we're using that's clean, and we've had to put energy into it to clean it. But now we have this wastewater that we're generating from manufacturing, from our homes. And this wastewater now has to use a lot of energy, 2%, in order to discharge it safely. And so, again, another area where these two fields are linked. And this is an area where I've done a lot of work, and where the field is doing a lot of work right now to try to change this and actually make wastewater treatment energy neutral. And so I want to start by talking about how wastewater treatment works, and how it contributes to climate change, just so that you can understand where the energy input is, and then how different groups are working to change that. How's it going so far? Is everyone with me? Okay, good. I see the thumbs up. Good. Okay. So what happens in a wastewater treatment plant? Here in the Twin Cities area, we separate our stormwater from our wastewater. This isn't the case in all cities. It's where most cities are trying to go, is to separate these. And so when there's a storm like we had yesterday and there's a lot of rain, that water goes straight to the Mississippi River. So it doesn't go through the wastewater treatment plant. What does go to the wastewater treatment plant is municipal wastewater. So this would be the wastewater that comes from our homes or from businesses, from the university, where I work. And so that wastewater would go to the wastewater treatment plant. And then a lot of industries also discharge their wastewater to the wastewater treatment plant. There are a couple in town that do their own wastewater treatment, 3M and always forget the new name of Coke refineries, even though they changed their name eons ago, but they treat their own wastewater. But most of the industries in town discharge their wastewater to the wastewater treatment plant. And so what happens is we blend these streams and then it gets treated. And I'll walk through that in a second. So in the wastewater treatment plant, once this wastewater gets there, there are a couple of different things that typically happen to it. The first thing that happens is what we call primary treatment. And in primary treatment, we're removing the solids that are present in that wastewater. And so for this, we just sit that wastewater in a big tank and let it sit for a few hours and let the solids just settle out. And so we settle out this material, and now this water is a little cleaner. It doesn't have the same solids in it, and we send that to the next treatment stage. And when we do this, we produce waste solids. And so this, if you think about the stuff that would be coming into a wastewater treatment plant, it's fecal matter, it's urine, but it's also dirt that might come off of clothing that you're washing. It might be ground up food that you're putting down a garbage disposal, which is not a good thing to do from an energy perspective. It might be shampoo, personal care products. We discharge things like hormones and medications that we take in our urine. And so all of this would be going into the wastewater treatment plant. And so you think about that and it seems really dirty, but it's actually pretty dilute stuff. And all of that material that comes in that contains carbon, organic carbon, that material is what we're trying to get rid of before we discharge this wastewater clean now to the environment. So once we've removed our solids, we go to secondary treatment. And in secondary treatment, we have a whole lot of bacteria, just tons of bacteria in a big tank. And that bacteria eats the organic matter, the carbon that comes in. And those bacteria also eat ammonia that's present. And in order to get the bacteria to do that, we feed them oxygen. So they function kind of like we do. We might eat a cookie and breathe air. They eat our waste and breathe oxygen, same as we do. And so when they do this, when they eat this material and breathe the oxygen, about a third to a half of the carbon that's in our waste goes to make more bacteria, goes to grow bacteria. And then the rest of it is discharged as CO2. So this is one of the first CO2 footprints. of the wastewater treatment plant that we've talked about so far, and that's that all the waste that comes in at the influent, um, about 2/3 of that will end up as CO2. Then we go to settling, and these bacteria that we've now grown settle out as waste solids. And so we have our waste solids that are coming out that we have to deal with, and then clean water that's coming out, and hopefully we've removed the nutrients that we need to. One thing that we also want to think about, so here's one of our CO2 impacts here. The other one is the energy use that takes place in a wastewater treatment plant. And the first thing you notice when you look at this graph, there are all sorts of different things that we're using energy for in our wastewater treatment plant. But the big one is this big orange piece of the pie. About half of the energy used in a wastewater treatment plant is used for aeration. And that aeration is the addition of this oxygen. And so we just take big blowers and we take air, we compress it, we blow it into these huge reactors filled with bacteria, and this uses an enormous amount of energy. And so looking at this, hopefully you're thinking, well, if there would be some way that we could get bacteria to do what we want them to do, but they don't have to breathe oxygen, then we might be in good shape, because then we would use much less energy. And so that's kind of where things are going. So other things that happen in a wastewater treatment plant, I mentioned that we blend the waste from municipalities and industries. And so I want to kind of dig into that for just a minute. If we look at this industrial waste, a lot of these industrial waste streams are carbon rich. They've got a lot of waste in them, a lot of organic carbon waste, but they're typically non-human contact waste streams. So they're pathogen free. They don't have hormones. They don't have medications that we take in them. So they're kind of nice waste streams. And some of these wastes, especially if they're high strength carbon rich wastes, they could be treated differently under anaerobic conditions, so no air addition, to recover that carbon as methane, which we can use as an energy source. So instead of in a standard wastewater treatment plant, if we go here and we blend it, then we've diluted it and we use energy to generate CO2. If we can treat it back up the stream, we can take this high strength wastewater and we can treat it in a different way that doesn't use energy or minimizes the use of energy, and we generate methane, which can then be used as an energy source from that. If we look at this municipal waste stream, these waste streams are dilute. They've got all of our shower water, our toilet flush water, our dishwater, all of that's in that waste stream. And it also contains potential pathogens, personal care products, all of these things that come out of our waste. And one thing to keep in mind with this is that nitrogen removal requires a lot of air addition. And so if we can treat this dilute waste stream without adding a bunch of strength from our industrial waste streams, we can probably do it better and with less energy addition. And so when we blend these, it makes resource recovery as methane from the industrial wastewater really difficult. It also makes nutrient removal harder, in particular nitrogen, and it makes treatment more energy intensive in general. And so what we've been doing when we combine these waste streams makes that carbon footprint much larger than it really needs to be. So I'm going to stop and blow everyone's pictures up again. Is everything good? Does it make sense so far? Yeah, okay, good. Okay. So we need to change the way that we treat wastewater to decrease or hopefully eliminate its contribution to climate change in terms of its high energy footprint and high carbon footprint. And so what are some options to improve practice? There's been a lot of interest and work lately on creating energy neutral wastewater treatment plants. And this is something that or even energy positive wastewater treatment plants. This is something that um, globally people are working on, and some of the more forward-looking wastewater treatment plants in the US are really interested in this. And some of the ways that we can do this, energy or efficiency improvements is a big one. So using LED lights, doing different things to make the system and the processes and the buildings more efficient. Using renewable energy in plant operations. So instead of using carbon based fuels, using solar, something like that. Energy recovery from waste solids. I showed you that we have those waste solids, so the solids that come in and then also the bacteria. We can take those waste streams and we can generate energy from those by treating those anaerobically and making methane as well. And so that's something that we could do. Wastewater's typically got a lot of heat associated with it, and there's been a lot of interest in using that heat to warm other waste or other water streams, so we don't waste that heat. Also, separating industrial treatment from municipal treatment and recovering energy from that industrial waste. And the last one is low energy nutrient removal. I mentioned that nitrogen treatment uses a lot of air, it uses a lot of energy, and there are new ways that we can think about removing nutrients using low energy methods. And now there's a lot more interest in recovering nutrients so that we can use it for something positive rather than fixing more nitrogen industrially and using that for fertilizer. And I would say that the wastewater industry is really working on all of these areas. Some plants are not working on any, and some plants are doing, I think, a great job working on all of these areas. One example just right up the road is St. Cloud. If you're looking for another speaker on wastewater, I definitely recommend Tracy Hodel. She's fantastic. And I think St. Cloud is doing so many cool things to really improve its energy footprint and really make itself energy positive. They have done a lot with respect to energy efficiency. Their plant is incredibly efficient. I'll show you a picture in a minute of their solar array. They generate a ton of energy from solar. They have a really unique program where they take industrial waste separate from their municipal waste. They don't blend the two, and they're using that to generate energy. They're generating energy from their waste solids and also recovering nutrients from their waste solids. And they've got a new project where they're generating hydrogen from electrolysis, which I believe is solar powered. And so they're really doing a lot of cool things in order to really kind of push the field forward in terms of wastewater. And this is just a picture. The bottom one is from St. Cloud, and this was given to me from by Tracy. And then the top one I took in Hutchinson, Minnesota. And Hutchinson is pretty rural. It's a small system. St. Cloud is big, and both of them are using solar really effectively in order to power their wastewater treatment plants. When we think about kind of what I do and what researchers are doing globally, there's a lot of research going on in wastewater, and a lot of that research is focused on energy recovery, also nutrient recovery, either from the municipal wastewater blended streams or from industrial waste streams separated, and then also low energy nutrient removal. And in my lab, we've been working on both of these areas for some time. And I'm just going to give you, checking the time, I'm just going to give you a quick tour of some of the stuff we're doing, and then I'll wrap it up. So some of the work that I've been doing has focused on this idea of encapsulation. So I love bacteria. I work with biological treatment processes. And with encapsulation, what we can do is we can retain very specific organisms. And so we can control how many organisms and which types of organisms we have. And then to some extent, we can protect those organisms and control their internal environment. And so we can get them to do what we want them to do. The other real benefit of encapsulation is you can see these pictures of these different encapsulants we've made in our lab. They're pretty big. And so if you think about bacteria, they're incredibly small. And if we have to rely on the bacteria to clump up and settle on their own, sometimes that doesn't work very well. And if instead we have these big beads, you can just very simply filter those out, or they settle pretty well, and you don't have to worry about pore separation. And so that's another advantage. And this is just a little video of a really early stage project that I'll show you the latest of in a minute. But these little beads in there, those are our encapsulants. And what we're doing here is we're treating brewery wastewater and generating hydrogen, which we're taking through a little fuel cell and running a fan with it. And so this is one of the focuses that we've got is generating hydrogen and methane from wastewater. And this is where the system is now. We have a pilot anaerobic treatment system at Fulton Brewing, and we're doing that to recover energy in the form of hydrogen and methane from their wastewater. And so these are our new encapsulants that we're using. These last a really long time, and they don't fall apart, and they retain the bacteria really effectively. And what we're experimenting right now is to see if a single stage system that generates only methane is better or worse than a two-stage system. And this little robot guy is our first stage reactor. This one generates hydrogen. And then you can kind of see back there in the corner another black reactor that looks just like this one. That's our methane reactor. And so in the two-stage system, we can kind of upgrade our methane gas a little bit by adding hydrogen to it. And so that's what we're trying to compare. And so we're just feeding wastewater into our reactors and monitoring what's going on. And then right now what we're doing is we're collecting our gas passively. You can sort of see these little bags back here. We have these tight bags that we plumb in. And so we're collecting the gas so we can measure how much the bacteria are generating and what kind of gas. And then we are working with some colleagues in mechanical engineering who, once we get good baseline data, are going to start actively extracting that gas to see if we can get more of that gas out. One of the things that you can imagine could be a problem, methane is a gas, but it's also reasonably soluble. And these waste streams are pretty warm, which does drive that methane out, but you still end up with a fair amount of methane dissolved in that liquid effluent after it's been treated. And so one of the things that we're really interested in is, can we do some sort of active extraction to pull out all of that methane, so we are using everything we're making and we're not making a worse greenhouse gas problem. We're also exploring ways to encourage low energy nutrient removal. And what we've been doing, I've been working with colleagues in chemistry and chemical engineering to develop supports that encourage the growth and retention of specialized bacteria that perform low energy ammonia treatment. And so there's just a little bit of oxygen that's needed. You don't need to add very much, and it uses about a third of the energy of traditional treatment. And so we've made these little pucks that basically absorb ammonia, and then the bacteria are attracted to that, and then they grow all over these pucks. And then we also have made membranes, which you can see here, and we grow a surface on there that attracts, again, the ammonium and then the bacteria, and then they colonize these membranes, and they use that ammonia more effectively. And so this is what we've been working on, and now we're actually moving these pucks out into stormwater treatment to see if they'll work effectively there. So that's it for my little tour. So I just want to finish up with kind of the bottom line. And these points are all either paraphrased or taken directly from the EPA. So these are the things we need to do. We need to have efficiency in the use of energy and water be the norm. We need to make sure we're using our energy really efficiently so that we're not wasting water and potentially causing ecological harm. We also then need to make sure that we're using our water effectively and efficiently so that we don't waste more energy cleaning that water. We need to develop energy resources in a way that has minimal impact on water, both in terms of quantity and quality. So things like fracking, where you're then contaminating that water. We need to think about better ways of extracting energy and using our energy resources so we're not damaging this other resource at the same time. The pumping, treating, distribution, use, collection, reuse, and ultimate disposal of water should have the smallest impact on energy resources as possible. So we need to be as efficient as possible. And where we can impact this is really in the use. And just thinking about water and its energy footprint when we're using that water. And then finally, wastewater treatment facilities should be viewed as renewable resource recovery facilities that produce clean water, which they pretty much do now, depending on what you're looking at. We can recover energy from that wastewater, and then we can also generate nutrients that can be used. And so that's it. Thank you, and happy to chat and answer questions. Tim, you have a question?
Have just an extra point. If, one of the problems we have with climate change is making our infrastructure resilient. Yeah. You ever notice where wastewater treatment facilities are? A lot of them are floodplains. So there's a lot of danger of flooding and then incapacitating those facilities. So you need to look at backup energy. You need to look at that whole scenario to make these systems much more resilient than they are. The other quick point is energy distribution. The piping is the largest part of energy. And a lot of our piping infrastructure, all you have to do is look at Duluth, is very antiquated. So we've got a lot of catching up to do just on building resilient infrastructure.
Yeah, those are great points. Thanks. Tim.
Okay, I want to quick make a shout out to Ryan Kiefer. He just joined our chapter yesterday. So welcome, Ryan. Then my question deals with nutrient recovery. You mentioned that's a focus. Well, how about human waste? Is there any progress in making it usable for, say, fertilizer? Or I know there's concerns there.
Yeah, there's a lot of work going on in that area. There's research. I'm not doing work on specifically human waste, but there are a lot of people that are doing work in an area that that's resource constrained. So thinking about countries in the global south that are maybe don't have access to sanitation. There's a lot of work going on there, trying to develop toilets where that human waste is either pasteurized or managed in some way where it then is safe to use directly as fertilizer. There's some nice research out there, actually, kind of bigger picture systems looking at how far you would need to go from different city centers or where the populations are to the agricultural areas in order to make that make more sense. And in a lot of the global south, those are pretty co-located, the population and the agriculture. In the US, we're pretty separated. The agriculture is far away from the population centers. So that's one thing. In the US, we've spent a lot of time trying to figure out how to make kind of clean nutrients. So that's in wastewater treatment. They can actually, and this is getting scaled up lots of places. Madison does this. A lot of places around are treating the waste solids in a way that they can then generate this very clean chemical that then can be used as a fertilizer that's got nitrogen and phosphorus in it. And it's called struvite. And people are really working a lot on that because there's that material then doesn't have any pathogens or anything like that in it. So that's another area.
Thank you.
Yeah. Jessica.
I think I had two questions. One, did I hear you mention hydrogen?
I did, yeah.
Can I, before I ask my question, is that green, blue, black? Like what hydrogen would that be considered?
Oh, I think it would I think it would be considered green hydrogen because it would be hydrogen generated from what happens is the bacteria take the waste and in the first stage of processing, they create acids. Those are the things that smell horrible. So butyrate and propionate and things like that. And then they also generate hydrogen at the same time. So it's one of their byproducts. It's
And then
kind of like,
how does the separation occur then?
yeah. So in that stage, they would be generating hydrogen and CO2. And so we would collect that gas. And so it would be mixed with both hydrogen and CO2. So it's not the way we've been doing it anyway, it's not a super pure stream of hydrogen. But we've worked with a guy in mechanical engineering who does combustion research. And so he's looked at like what the optimal blend is of this like hydrogen CO2 stream with methane so that you can actually get more energy out of it. So yeah, so it's not a clean hydrogen stream, I would say, but it's I think it would be considered green.
Well, so then are you burning the CO2 and the methane?
Yeah, so you would burn, yeah, you would use the CO2 and the methane. The CO2 won't burn, but methane and hydrogen, you would use those for energy production. So instead of like the brewery buying energy to heat their tanks, they would burn the energy that they're generating from their wastewater to heat their tanks.
Even though methane is a more destructive, like as a GHG.
It's a horrible greenhouse gas,
Yeah.
but if you burn it, then you're releasing CO2. So as long as you're capturing it effectively, you're good.
Okay, thank you for answering that question.
Sure.
Is it okay for me to ask a second question?
I don't mind.
I just want to make sure we have time and everybody else has the time to get the floor. Okay, thank you, Tim. My other question was like more nature-based solutions. What, if anything, is like on the docket, or what you guys are planning, if there's anything you're planning on scaling up or anything along those lines.
Yeah, so people are working on nature-based solutions in general. I've done a little bit of work on them in terms of stormwater treatment. So looking at rain gardens and things like that. People have been looking at nature-based solutions for usually not all the wastewater treatment, but they'll put it at the end of the wastewater treatment plant. I mentioned the things like hormones and pharmaceuticals that are in the wastewater. And I also said that there was clean water coming out the end. Sometimes the water coming out the end still has hormones, pharmaceuticals, medications in it. And so nature-based solutions have been pretty effective at removing those types of things through bacterial action for the most part. A little bit gets taken up in the plants, but it's mainly bacteria. Yeah.
Thank you.
Sure.
I have a question. Can anybody hear me?
Yep.
Yeah, this is Richard Venberg. I live in the neighborhood Como Southeast, which is just north of the University of Minnesota's main campus. 3-4 years ago, we put in a stormwater runoff garden on one of our, it's a unique neighborhood in the metro area. We have dog legs. So you enter on 15th, you turn left and you come out on 16th.
Okay.
People are always getting lost. There's 4 or 5 of them in a row on Talmadge Avenue.
Okay.
And so we put in the stormwater runoff garden. And I was wondering if you had any experience with those, because it seems to me when we get a heavy rain, the entire block is flooded because it slows down the drain. Mm-hmm. And then it's filtered, naturally through earth before it gets to, I guess, a sewer somewhere and dumps into the Mississippi. But we found we have no way of measuring the effectiveness. How many hundreds of thousands of gallons of rainwater is it filtering, and what's coming out the end? Like
Yeah,
you just mentioned, it's probably taken out some big chunks. I don't know if, lead floating around in there. I can't imagine there's many hormones or prescription drugs because it is mostly rainwater.
right.
And it's just, the junk that falls off cars.
Yeah.
All those weird things that come off tires and tailpipes and all that.
Yeah. So there are a couple people that know a whole lot more than me about that. One of them, Andy Erickson, is at the university. He works at the St. Anthony Falls lab, and he's a stormwater expert. What I know about it is a lot of these nature-based solutions, including the stormwater ones, but then also the wastewater ones, we've done, I say we, I'm not one of them. People have done studies, they've done research to look at how things are moving, but it's usually a very idealized situation where you have pretty good control and you know exactly what's coming in, you know how the flow goes, and you know exactly how it's going out. The system's been designed just right, and it's got sampling ports in there, maybe sensors. And so that's where we know a lot of the data from, and we can say, in these conditions or these certain situations, they work well. There's not a whole lot of data on these nature-based solutions in general. And so, and also, I'm not sure how well they work in practice. If it's not, I did some work on rain gardens, but we had these columns, and so you knew exactly what was coming in, and all of it was contacted by the plants, and I don't think that's quite the situation in a real rain garden. And so I think more needs to be done to understand exactly what they're filtering out. From the work we did, it looked like they filtered out PAHs, which are petroleum hydrocarbons that are in roof shingles and asphalt that runs off. They did a pretty good job at that.
Well, those are pretty big particles, though, aren't they?
Well, it's a chemical, so it'd be dissolved.
Oh, okay.
Yeah. But they stick and then they get eaten up by the bacteria. So it's like kind of a two-stage system. They work pretty well on particles and then chemicals that stick to the particles. Nitrogen sometimes is exported in higher concentrations from those. So it depends on the system. But I would say, if you guys are interested in stormwater, Andy Erickson would be a great person to have come and talk, because he's really knowledgeable, and I think he could answer a lot more of this than I can.
Yeah. You said Andy Erickson?
Erickson, yeah, I can put his name in the chat.
Yeah, I'd like to get a hold of him because when it was going in 3-4 years ago, there was a lot of controversy around it. And the main one was, how do we know that it's doing anything at all? Because there had been a berm there, which was a traffic slowing device that was put in like 1945. So it was raised 3-4 feet. So when a car missed the turn, it would collide into some dirt, and that was good. But they dug that out because it has to be below grade, so it flows in there. And then they put in 15 8-inch diameter steel and concrete pipes. So how many decades was my question, to pay off the carbon footprint of constructing the natural system?
Yeah.
And one car collided into, several cars have already hit it. And so they're all at different angles instead of vertical. So visually it's an eyesore, but if it's doing great stuff, I can get past that,
Yeah. Yeah.
But
Richard, you raise a really good point about kind of the carbon footprint of these technologies. And that's with the encapsulation work we've been doing. We've been working with a colleague at University of Illinois, and he specializes in that, where he looks at how much carbon and energy is associated with manufacturing those little encapsulants? How much is associated with manufacturing a concrete reactor? How much is associated with pumping the water? How much is associated with if we do active gas capture so we can get all that methane out of the effluent? How much energy is associated with that? And so I think it's been incredibly instructive to me to think about, okay, what do we need to work on? Because if this is here, it's not carbon neutral, and if it's here, it is. And so that's been really fantastic. And I think in a way, those exercises are maybe not always grounded in reality, but I think they're always good exercises to go through, because then you can really see if what you're trying to do will move the needle on what we really want to move the needle on, which is carbon emissions and total carbon emissions. And so I think that's really a great way of thinking about it.
Okay.
Yeah.
Thank you.
Sure. Jason?
Thanks, Paige, for a great talk, by the way.
Thank you.
I just had a really quick question. We've kind of been talking a lot about water that is, flowing from one place to another or being treated. I kind of wondered, what about water that is just sort of sitting around? And I guess maybe I'm thinking mostly like, animal feedlots or the animal containment ponds that kind of hang around. Is this technology you guys are developing, does it have application for that as well, or kind of along the same lines?
Yeah, that's a great question. So you're thinking about kind of those like lagoons, the big pits of waste?
Exactly.
Yeah. I think that this would probably not be a great solution. The encapsulation would probably not be a great solution for that, because I think it'd be over-engineered. It'd be too expensive. It would be more than they need. But the same anaerobic processes that we're getting to happen, but putting them in like a little bead, you can do that still in those lagoons. And there are people that have been working on, how can we really take that animal waste and extract nutrients from it, and then also energy from it, and not do what Jessica mentioned, which is treat it in a big open pond where methane goes up into the atmosphere, which was, kind of a disaster. Yeah.
Okay. Thank you.
Yeah.
Okay. Well, we're coming up on 7:30. We probably have time for one more question if anyone has one. In the meantime, why don't we give Paige? Go ahead.
I'll take that opportunity. I was wondering if you had any thoughts at the micro scale for individuals who are looking to either treat wastewater or like in natural ways, or collect water, if there's any thoughts that you wanted to share with us.
Well, the one I mentioned is garbage disposals. Don't use garbage disposal. Take compost. When you use garbage disposal, you send a bunch of carbon down into the wastewater treatment plant that then has to be treated. And so I think if you can think about composting, that's much better choice. Just generally using less water as you can. People have put in systems where they collect the water from their clothing washers, so their washing machines. And so a lot of times, that water, for us anyway, we've got a big sink in the basement and it goes into the big sink. And so you could put a tub under there and you could collect that water and use it for, this year we don't need it, but for watering your plants and your.
I heard that can be great, but with all the extra toxins that are now put in our clothes, that's like, forget detergents, like
the micro silver and microplastics and all of that. Okay. So you have to know what you're washing. I guess I would
say by natural is what you're saying.
I wouldn't put nano silver and stuff in. What else would I say? Those are big ones. Yeah, and I guess the other thing is think about the products you're buying and using. So kind of along what you were just mentioning about clothing, a lot of clothes have coatings or additives, flame retardants. I know when my kids were little, it was really hard to find the pajamas that didn't have the flame retardants in it. Thinking about what you, the products you use, you know, on your body and wash down the drain. Triclosan's been banned in Minnesota, but for a while, you know, it was in this antibacterial hand soap, which we don't need. And so thinking about like what products you're using is always a good thing too, because that just makes this water that we're then discharging cleaner for the people downstream to use. Yeah.
Okay, well, we reached the end of our meeting. Let's give a big hand for Paige. It's really an excellent talk.
Thank you.